So, hi again. So, you all know about me now. So, I had a background in machine learning and speech processing as I did my master's in San Diego State in electrical and computer engineering. And after that, I worked for Qualcomm a little bit for over 3 years before I moved here. So, I have some research and thesis experience with Hidden Markov Models, so I thought I could share my knowledge with you here. So this is the agenda that we talk about. Just going to talk about a little bit about machine learning and then jump to Hidden Markov Models. And I will be giving some examples of Hidden Markov Models, including a real life example, which is speech recognition and speech processing, which we use in our everyday lives right now. And 3 fundamental problems and algorithms of Hidden Markov Models. And I also did a hobby project in my research. So I used to synthesize music, like how we synthesize speech and recognize speech. Likewise, I was trying to synthesize music by building Hidden Markov Models. So at the end, I'm just going to show a demo. It's not proper, but still, it sounds like music, so that's a win. And also, I'm going to give some information on how to build it, like the toolkits that's available to build these Hidden Markov Models. So is anyone new to machine learning or? Okay, sure. So machine learning is just like, so it's basically teaching and training the machines and computers to predict and think and make decisions like how humans make. So for that, we use existing data set and build some complex algorithms. So based on the models that we build, we can use whatever new we get. For example, any kind of new speech. We are not like programmatically, we haven't programmed on detecting speech. Like if we speak to a Siri, no one has programmed what we speak to recognize that. So it's all based on some sort of model, some intelligent model. So with existing data, it just like predicts what it could be based on some language models, some grammar. So that's how machine learning works. So this kind of I'm going to jump into what is Hidden Markov Models. So before that, these are the basic applications where it's used, like gesture recognition, speech recognition, handwriting recognition, language modeling, stock pay prediction, and a lot more. So what is Hidden Markov Model and where do we actually use it? So it is a statistical model. So if we do not know the states of some events, if we are able to make some observation, we could be able to predict the states. So I'm just going to tell this with a very simple example. So for example, if you want to predict the mood of a person or like mood of your wife, you could find something that is correlated to that mood, like the habits of it. For example, if your wife like clenches or grinds her teeth while she's angry, so by making some observation, which is like clenching or grinding the teeth, you could predict her mood, whether she's angry, whether she's sad, whether she's happy. So here are the states, which is actually the mood or the emotional state of a person. This is hidden here. What we could see is the observation, something correlated to it, which is like clenching or grinding the teeth. So based on the observation, we could predict the model, we could predict what states it has actually transitioned in that. So in the diagram here, you could see x of t minus 1, x of t, and all these variables. So y is basically the output observation that we could make, which is, as I said, clenching or grinding the teeth, and x is the actual state which we want to predict, which is the mood. So it also changes over time. So t is like time, so in terms of time it changes over time. So based on the observation sequences, we could actually predict the hidden states of the model. So before jumping to where to use these, I could also tell a couple more examples about it so that it would be easy to digest this concept before going more into technical details. So this is like one of the most commonly used example of hidden Markov model. So first we need to think what is a hidden Markov model and what is not. For example, if you take a single coin, if you toss it, you could make two observations. It could be either a head or a tail. And you'll be pretty sure whatever observation you see that has come actually from that single coin that you tossed. So this is definitely not a hidden Markov model because here we have the observation. So based on these observations, you are pretty sure it all came from the coin one. So this is an observable Markov model and this is not hidden. But if you consider like 2-coin model or a 3-coin model, if you toss 2 coins and if you just have the observations of the coin toss, which is like head, head, tails, tails, there is something hidden in this. Like the observation you made, head could come from coin 2 or it could come from the first coin. So there is something hidden in this model. So you could call this as a hidden Markov model. Likewise, a 3-coin model, you could call that as a hidden Markov model. Or another example would be like to predict the weather based on the observation. The observation would be like, for example, if you have no idea what the weather is outside, but you could say that by observing what people coming inside wears, like whether they wear shorts, whether they carry umbrella, or whether they wear jacket. Based on the observations, you could actually predict the states of the model. So weather prediction belongs to hidden Markov models. So I guess now you have some basic idea about hidden Markov models. Do you have any questions to here? Do you want more examples or what hidden Markov models are?
Still don't get it. Seriously. Go on. These things come to me.
No, but
Give maybe an example of what like a data structure involved in this might look like. How do you organize your information to use for a hidden Markov model? Like
yeah.
just like, you know, so you got heads and tails, so that's like, you know, AB and whatever.
Right, sure. I have.
No, I just asked because I think, I mean, it'll sort of help me a bit, maybe help others, you know, get a sense of what we're really working on.
Yeah, sure. For example, let's just take the coin toss model. Here, when you toss 2 coins, you get head, tails. All you could observe is, I mean, for example, there are 2 persons. One person is tossing the coin. Other person is just like making notes of what the results are. Other person doesn't know whether the result came from first coin or second coin. So this person is just tossing 1 coin at a time. So if I have 2 coins in my hand, if I just like toss 1 coin, I'm just telling the observation that I got a head, but others don't know whether that observation came from the first coin or the second coin. So using this hidden Markov model, we could actually predict the state of how the output, where the observation came from. So for example, if you consider this picture, these are the observations that you could see. With that, you could predict what states are, I mean, how it came from these states based on some probability. So this is a stochastic model used to predict this. So are you comfortable till now? So we are going to predict the states based on whatever we currently have. For example, let me jump back to the first example I told about predicting the mood based on the actions like clenching or grinding the teeth. If you know the probability of, for example, 50% of the time if your wife grinds her teeth, if you have that probability information, or you could base, or for example, for each minute how she changes her mood, if you have that information, like how the state changes from time to time, how it changes over time. If you have that information, and if you have the observation information, you could actually predict the mood. So here, for example, if X is the hidden state and Y is the observation that is correlated with the state, you could predict X. So we could predict this based on calculating 3 probabilities, like a start probability, an emission probability, and a transition probability. So start probability is like, what are the chances of starting in the state? For example, if you consider speech recognition, a sentence could be started in I, but it could not be started with the word of. So that would be like the start probability. What is the probability of something getting started in a particular state? The emission probability would be like, what are the chances of each observation? Like, in the first example I said, what are the chances of observing your wife clenching her teeth when she's angry? Maybe she is clenching her teeth because she has a TMJ. It doesn't necessarily mean that she's angry, but that is the emission probability. Like, what are the chances of observing something in a particular state? And transition probability would be like the probability of the states changing from one state to another. For example, in a sentence, you are awesome. What are the chances of the word, what are the chances for are to appear after you? Or, for example, there could not be any sentences like you of awesome. So that has less probability compared to you are awesome. So that is transition probability, like the probability of how one state could be transitioned to another. So now let's just like concentrate on one specific example, which is like speech recognition systems. So this is a speech waveform that is given like in time space, but if this is the Fourier transform of that, which is like in frequency space. So speech is basically collection of sentences. If you just like break that up, it will be like words. If you break words, it will be just like phenoms. So each small unit will be a hidden Markov model here. So this is a speech waveform. She just had a baby. So if you just like break that, each word can be formed as a hidden Markov model. If you just split this, each word, we have phenoms. Each one could be designed as hidden Markov model. That is the basic idea. So, okay, we have the word of. This is the hidden Markov model of the word of. So it could be pronounced in like different ways. You could pronounce it as like of, or you could pronounce it as of. So these are the transitions of how it could reach from one state to another. So this is like the start and the end of the hidden Markov model. It could either go through this path or it could go through this path. So this is how you could construct a model for a particular word. Likewise, you could, for example, if you are thinking about different digits, these are different digits. This is the start and end of the hidden Markov model. For the word one, this is how it transitions, like or for 8, it's like 8. So each one is a hidden Markov model. So the way speech recognition works is we have a speech waveform, so it will just see how the waveform could correlate best to each word. How the part of a waveform could easily correlate to a phenom. So if you just like think about the whole speech waveform, just like segment that, it would just find the best correlation between that waveform to the phenom. And it just combines everything together, and based on the language models and grammar, it sees what best fits into the next word. That's how speech is recognized.
Is it forward only? Or
Sorry?
does it only go forwards, or does it have the ability to say, I made a mistake and come back to like another, like there was 70% chance that it was SH and CH
Right.
was 3% chance, and come back and say, oh, I screwed up, down here, and
Right.
kind of restart the
So
path.
it re-estimates it. So if it doesn't, like after 3 words, if it realizes, the parameters get re-estimated. But again, that depends from model to model. Some model are like, it's a hybrid model, which could re-estimate. Some are like very basic, simple models, which are just like forward algorithms.
If you've ever watched Apple's speech recognition on the iPhone, you can actually see it doing that as you're speaking to it. It'll go back and change words that are earlier that
Right.
it had already recognized, so it'll go back and be like, no, that doesn't fit, and it'll change it on you. Sometimes for the better.
So now we have like, this hidden Markov model is like very old. It started in like 1970s, but it's still powerful and still used. But nowadays it's like combined with deep neural networks and other complex algorithms. So now it just like corrects, estimate the parameters and give proper recognition. So if we have like a speech waveform first, we have features for each waveform in frequency domain. So it just extracts a feature and it just compares what best correlates with each phoneme. And likewise, it recognizes it. I could go into more detail. So just another example. This is like, he is new, how the hidden Markov model is there for the sentence. So the aim is we are finding the probability of the word given a speech waveform. So for example, the W is the word and A is the acoustic waveform. So probability of finding the word given the speech waveform will be, this is a training set. Like previously we would have trained a lot of phonemes of like, for example, we would have trained that this waveform belongs to this phoneme. So based on the training set here, and based on the language model and grammar, so P of W is like, it's a probability of occurring that a word could occur. So that's like based on English grammar and language models. And based on that training set, we could estimate the probability of getting the word given a speech waveform. So this recognition basically consists of two processes. First would be like the training set and then it recognizes. So in training, we will have like, if you visit like the HTK Cambridge website, they have like 100 million trained words in different languages actually. So for each word, they would have the corresponding feature vectors and they would have trained that to form hidden Markov models. So even if you want to build a new algorithm, you could use all the existing training set. That's how the current words, any new sentence is predicted based on existing training set. So in the training set, each phoneme is trained, and most popular or complicated words are trained. And in the recognition phase, it just sees, like from the speech waveform, it extracts the feature, is like we call it as Mills abstract features. It extracts all the feature vectors and it computes different sort of probabilities. I will explain about this in the next slides. So you will just compute the probability of having that word given the speech waveform. And it selects what word would best fit in the part of the sentence that it's going to form.
Can I ask a question?
Sure.
It's about the slide, 2 slides before. We had the formula. Yeah. So that's like the Bayes formula, right?
Yeah, that's Bayes theorem. That's correct.
In Bayes theorem, given different names, you're using the emissions probability, transition probability, and starting probability.
Correct.
Can you point to which? Is this just the?
I have it somewhere here. Let's just get it. Yeah, I have it here. So, actually, like, calculating the forward, backward probability, everything is emission probability, it's all like different formulas.
So those don't, that Bayes isn't used for that part. That's a Markov process.
It does use, but this is being. I think I can. I don't have it in the slide, but basically, for example, if I take this, so this would be the transition probabilities, and it would just multiply with each of the states here. So there's a derivation for that. so I don't have it in my slide, but definitely we could talk about this again.
Okay,
So as I already talked about the emission and transition probability, so the transition probability will be how probable it is for one word to transition to the next one, and the emission probability will be how probably would a word occur given the speech waveform. So here, so initial probability will be like how probable it is to start with the particular word, that will be the initial probability. So these are like the general notations of the state transition. So the state transition will be like, if you see this diagram, if you have this as A, then each one is like Aij will be like A11, A22, A23, likewise. I didn't jump much into derivation of that or the mathematical part. I just want to leave it generic right now, but if someone is interested, we could continue that as part 2 or something.
so these are bound to words, or do you have transition probabilities that cover like beyond boundaries to probabilities for, like you were talking about the,
Phoenix?
well, like deep neural networks tend to go like a long, short-term memory model and kind of look back in time and say, well, now this is a completely unlikely phrase, so I'm going to go back and like with
Right.
this whole batch of data,
Right.
re-estimate what's the more likely phrase, but it makes errors in small future steps, but then once it has more, do you have this in the HMM where you start moving beyond, to something that's like a phrasal level?
So with the pure hidden Markov model, there is no feedback, but with the hybrid ones, when we combine it, or
Even without feedback, you just have higher level models where you really count phrases instead of just use lower level. Like you have grammars for how words can be formed, but you also have grammars for how phrases can be formed.
Correct.
Sentences.
correct. So even in hidden Markov models, those phrases can be formed. Depends on what your model is. Your model could be a fill-in model, or your model could be a word model, or even your model could be a sentence model. Like when I played with music, instead of just training it with a single note, I could play it with like a 5-note pattern, and I could train the model with that. You would just see after this 5 notes how likely the next 5 notes are to occur. So it depends on what model you have decided to, what your training data set is. So basically, this hidden Markov model is to solve 3 problems: evaluation, decoding, and learning. So evaluation is like, if we have a model, we could compute how probable we get a particular output sequence. Or in decoding problem, if we have a model and if we have an output sequence, we could find the most likely sequence that could have generated that particular output sequence. Like we could actually see the path it could have traversed to reach the endpoint. Or in learning model, we will have a particular set of trained output sequences. We already have a trained set of all the initial emission probability. We could find how the future set is going to be, how the future states are going to be. So diagrammatically, in like the first problem, which is evaluation problem, this is the forward algorithm. So we have all the state sequences, we have the model. We could estimate what the output is going to be, like what the output observation could be. Or in the second one, the decoding problem, we could use this algorithm, Viterbi algorithm, to see, for example, if we have all the output sequence, we could find the most likely path it actually travels to reach that output. So each one would have like the best path factor, so it just chooses, ultimately it just finds out what the best path to reach that output sequence would be. Or this is the most common used one for speech recognition. This is for learning model. So just consider this part where the red ones are the training data set. You already know a particular set of parameters. You could estimate the future ones by estimating the parameters for that. Like how likely it is to traverse through the future path. So I use this model to generate music. So first I just like took a multi-track music piece, just split that into single notes and fed that into the model. And with the existing musical pieces and music knowledge, it could actually see how likely the next note is to occur and was able to synthesize music out of it. It's not great, but it's listenable. Does it sound familiar?
Mary had a little limp.
It sounds a little like Ode to Joy in some
Yeah,
parts.
you're right.
Yeah. Yeah.
So I just fed some Beethoven knowledge to it. And
So that's like when you just tap the middle suggested word to see what sentence it writes.
yeah. So this is how I was able to generate the music. Here, this part is a hidden Markov model. Like I had the musical notes, like separate individual notes, and one note could be played in like 50 different ways. So, or n number of ways. So I calculated, like I extracted features from that, and I initialized hidden Markov models, computed some mean and variance for each node, and using the best path, I was able to evaluate the using the VDRP algorithm, I was able to determine the best path. And using the learning algorithm, I was able to estimate the parameters. I was able to build a cluster hidden Markov model, and using some filters, I was able to generate the music. So this is what we actually need. These part, we could just consider them as black box, and we have hidden Markov model tool called as
Bless you.
HTK toolkit that has all these functions. Like HNet is, you could call HNet that does the first initialization, or HREST could do the learning, like the estimation of all the parameters. Likewise, you have like a lot of, it's here. You have a lot of, in the toolkit you could use anything. So this is the link to the toolkit and the speech user system. Actually, I just observed you also have not exactly these calls, but you could build hidden Markov models using TensorFlow. There are libraries to it. But this is what I use, and it's really great. Anyone wants to try. So just summarizing that, here is a speech. Consider these are the feature vectors extracted from the speech, and to recognize S1, S2, S3 are what we would like to recognize from the waveforms. So it would correlate this each bit of waveform that could best match with each phenom, and it could estimate that. And these are the library. This is how you could do. First, you could estimate the parameters using HNet, and you could estimate all the parameters like the emission probability, everything using HREST. And this is used to re-estimate all the parameters, and you could form hidden Markov models by following the sequence of making calls. And that's all I have for today.
What is your feature how were you summing your feature vectors for the keynotes? Like what do those
Extracting
look
the
like?
feature vectors?
Yeah, like what's,
So there's a library called for extracting each different feature vectors. So it sends it through a filter and it would determine the pitch for music, for example, or even for speech. It determines the energy, frequency, pitch, all the values from that waveform, and it could give a particular. It could just check out a value out of it. So
so that's something
based on the
that's already
duration,
trained
also it actually gives the feature vectors.
Is that something that is kind of an input to the whole system rather than something that's part of your process, I presume?
Correct. Yeah, feature vectors are the input to the system, because otherwise our speech or anything could be just .wave files. But there are libraries that could transform your wave file to feature vectors. Like MFCC is one of them. Any other questions?
On a slide way back, there, you talked about a state transition, and then it said Markov. It said it was state and time, and then in parentheses it said Markov. So, what is Markov itself? Like, what's the definition of that?
So Markov is something if a current output is based on the past output, that is a Markov model. If you could determine something at present based on the future, based on the past, that is a Markov. If you could estimate something in the future based on current, it's a Markov model. And here it is hidden because we actually do not know the states, but we have some observation that is coming from the state. So that's why this is hidden Markov model.
I think the argument is you only need to know one step back in the past to be able to predict the next current state, instead of other models require a long-running history to get a sense of like where the trajectory is going. That argument is that you can always sum the probability of what's going to happen next based on only having to look one step back, which is a simplifying assumption.
Yeah, true. You just assume you know the previous, just the immediate previous sequence of it.
Is Markov someone's name?
Yeah, the one who initially created that model as Markov. So
Yeah, I would have started with
it's
that.
also called as Markov assumptions. He also built this model based on some assumptions.
I remember using a Ruby library a long time ago to generate test sentences, and it was a Markov chain. Is
Correct.
this basically
Yeah, that's
the
the
same
same.
thing?
That's the same. Yes.
Would that be,
So this is also used to, so you're trying to guess the thing that you can't see with the things you can see.
Exactly.
This is also, once you've guessed the state that's hidden, tell you what's coming next. Like, your model says, my wife's teeth are clenched, I should duck.
Maybe that's the application of it.
Does that, I don't know, it seems like in general, I mean, this might be a good thing for countries to use at the UN. You know, you got all these signals, these hidden facts, and the public facts, and what comes next. And,
Right.
Now, you did show coin flips.
Yeah.
As one of the items. Now, I didn't quite get the inference on what could be assumed based off what was observed, because in the statistical modeling of coin flips, each flip is completely independent of any previous flips.
Right.
So how does that work with, it should, the math of it should work out to
It was the
no
story,
inference at all.
was the story is that
Correct.
you did
It's just a story, but you are right. But it's just like basic assumption that though each one is an independent flip, there is a probability. Even if you play poker, there is a probability of how much consecutive wins you get. Likewise, there's a probability associated, like how much consecutive heads you could get or consecutive tails you could get.
In a large sample size, yes.
Yeah, but definitely not on two.
Not based
That was
off the
just
last
for
one, okay.
yeah, because in two it's all like fixed.
Numbers,
I didn't
You're
know
right.
if there was some story about you knew at least 1 or 2 coins was weighted, and so you were trying to guess what you thought, which one was If it was weighted, one was weighted heavily towards heads, if you saw heads, then you have ridiculous,
So that, yeah,
Yeah,
otherwise it's 50/50.
correct,
Is it
correct.
a hidden Markov model, does not necessarily a very useful hidden Markov model?
Yeah, it would just, the matrix would be equally weighted everywhere, like two uncorrelated variables.
Right, but that is just like we used to think about the idea of how each observation could come from a sequence which we actually do not know. It could come from first coin or the second coin or the third coin. We just know all the observations. Just to digest that fact initially, I just use that as an example.
For speech, how large is the probability matrix going to be for all the phenoms? And how big of a thing in memory is this that we're going to be computing to do speech recognition?
So, to train for better accuracy, you at least need a corpus that consists of more than 50,000 samples.
And the sample would not just be, one sample is not one phenom, the sample is going to be like a sentence or a word? Is it like, what would that?
Yeah, sure. If you have at least more 100,000 phenoms, you could recognize the word. Like, for example, for this music, I trained that on 50,000 notes, musical notes. So if you do more, you could recognize and make better models.
And the output model you have, that's just a single matrix that's
Yeah.
what's the dimensionality of that look like?
So that was just, I don't know about the matrix, but because I just converted all the feature vectors